So today I'm going to give a presentation about our project, which is a data-driven framework for task recognition via wearable sensors for electric and gas workers. And this is a collaboration with my supervisor and my mentors, Dr. Sahand and Dr. Kabuto. Okay, based on statistics, electrical line workers and also oil and gas workers, they are among the top 10 most dangerous jobs in the United States. And there are so many reasons for this, but among them, lack of adequate supervision and lack of planning and prevention, which is also related to lack of supervision, are among the most important reasons. But fortunately, in past decade, technology and specifically IoT and more specifically wearable sensors has made supervision much easier. So motivated by this, we designed this framework that I'm going to describe. So jobs like electrical line workers and gas workers, they have some specific work domain characteristics. For example, they have remote work, they have unstructured tasks, they have some tasks that they are often performed at height. They may have heavy physical loads. And regarding those characteristics, we have some information needs. For example, we want to know what tasks they are doing, how long they are doing those tasks for, how many times per task do we have, and how they are doing those tasks. And using these information needs, we are gonna use them for management and also worker information uses. For example, we can have risk assessment, productivity evaluation, worker training, work assignment, and also predictive scheduling. And finally, we are going to have real-time coaching, safety alerts, and also performance feedback. And this is kind of the supervision that I mentioned earlier. Okay, so our objective is to use wearable sensor and statistical learning to classify the tasks performed by electrical workers and also gas workers. But in order to get to this objective, we are facing some challenges. First of all, there is variety and complexity in the tasks that these workers are doing. And secondly, there are some heterogeneities in this area, which is gonna make the classification performance, it's gonna degrade the classification performance. So in order to deal with these challenges, we are gonna use two approaches. Actually, we developed two approaches. So firstly, we are gonna investigate how features from a single wrist-worn accelerometer can be used to classify tasks performed by electrical line workers and gas workers. And secondly, we are gonna use transfer learning to investigate how these heterogeneities can impact the classification performance. And by those heterogeneities, we can have cross-sensor heterogeneity, cross-subject heterogeneity, and also cross-scenario heterogeneity. So cross-sensor heterogeneity is when we are using two sensors and they are different. So if the model is based on trained based on one sensor and it's tested on another sensor, so that heterogeneity can make problem for us. Or when we have different subjects, so that can be problematic as well. And cross-scenario heterogeneity, so this is a term that we are using, but basically, let's say we are training our model based on a lab environment, and then we are gonna use it in a real world. So that heterogeneity also can be problematic. Okay, so here you can see a literature review on occupational activity recognition. So to the best of our knowledge so far, there has been no research focusing on activity recognition on electrical line workers. So because of that, here we are doing an overall literature review. And here you can see that different researchers, they focus on sensor placement on different parts of the body. So you can see that there are some researchers that they use multiple locations for sensor placement, and that means that they are going to have multiple sensors. And we are not interested in those strategies because multiple sensors means being more obtrusive, and which is not good for us. And also these numbers that you can see in these circles, they are number of researchers focusing on that location. And we have sometimes blue circles and white circles. So blue circles means that the number of tasks being studied by those researchers are less than or equal to 5, so they are not complex cases. But white circles are the cases which focus on more than 5 tests. And these are, we are interested in these kind of researchers in this area because electrical line workers and gas workers, they have complex tasks. They have many tasks being performed in their shift. So if you look at this figure, you can see that most of them are blue. So most of them are focusing on simple tasks. Just a few of them are focusing on complex tasks, and among them, you can see that this area, which is risk, so in this area, there has been no research done so far. And we are interested in this one because of many reasons, but the most important reason is that a wristband sensor is not obtrusive at all. Okay, now you can see our proposed framework. First of all, we have data collection part. So in our case, we have 37 subjects, and you can see their information here. In our case, we use Empatica sensor and Maxim sensor to get the acceleration data. And at the end, we can use just one single sensor to be less obtrusive. But here we are using two sensors to kind of study the heterogeneity among different sensors. In this figure, you can see an illustration of our simulated lab environment. And here we can see the tasks being performed by people. For example, we have two scenarios. The first one is separate scenario, and the second one is mixed scenario. So in first one, you can see that we can have sitting, standing, walking. So these ones are duration, based on duration, and we can have some other tasks like climbing a ladder, which is repetition based, okay? And here we also have mixed scenario. So mixed scenario is basically similar to this one, but the tasks are being done with shorter duration. And for example, if we have 20 reps of climbing a ladder, so here we are gonna have just one repetition. And the reason behind this is that here we are trying to kind of mimic reality, because in reality it's more common to do one repetition rather than doing 20 repetition, which is more common in activity recognition literature. And the other difference is that here we are having this circuit, which is again more like reality. Okay, here we can see our approach one, the framework for our approach one. So as I mentioned, firstly, we have data collection based on Empatica sensor. We get acceleration data from it. And after that, we have database creation. After getting the database, we have model extraction phase, in which firstly, we have data pre-processing. Then we have feature engineering. So in this case, we have three types of features. The first one is mostly Fourier transforms, which is just frequency features. Then we have time domain features. And after that, we have wavelet features, which are both time and frequency features. So after getting the features, we do modeling, in which we are using three conventional classifiers. The first one is KNN, second one is random forest, and also we have SVM. And after doing this, we are going to evaluate our model. So this was our first approach. And secondly, we have approach two. And similarly, in the first step, we have data collection. But here, the difference is that we are simulating some heterogeneities. For example, you can see that we are using two sensors to have heterogeneity and be able to study heterogeneity. Then we have different subjects, again, to have cross-subject heterogeneity. And you can see that we have heterogeneity between lab environment and real world environment. So this is not exactly real world, but here we are trying to mimic real world environment. So after that, we have phase two, which is analysis. And here we are using transfer learning to kind of deal with the heterogeneity that we are facing here. And after using transfer learning, we are gonna benchmark that transfer learning against a very conventional method, which is SVM, and it's shown here. After phase two, it's time to do decision making. So if our conventional baseline, which is SVM, is better than transfer learning, so in that case, heterogeneity is not that important and we are good. So if our transfer learning is outperforming our conventional baseline, which is SVM, in that case, heterogeneity is important and transfer learning can be helpful. And finally, if both transfer learning and our baseline, they're not doing good. So in that case, another problem, which is not heterogeneity, is degrading the results. So in that case, we need to find those reasons which is out of the scope of our research. Okay, so here we can see the results for approach one. This is inter-subject classification. You can see that we have different features, for example, time domain features, frequency domain features, and also time frequency features. We are using different models. Here we can see task-specific performance, which is based on F1 score for each task. Okay, so here we can see the different tasks. For example, and these are abbreviations. For example, ladder is like climbing a ladder. And finally, you can see the overall accuracy for all of these methods. So obviously, time frequency features, it's outperforming our methods because it's showing highest accuracy here. And also you can see that these features are robust to the type of model, because for different models, which are KNN, SVN, and random forest, we are getting very good accuracies. But still, random forest and SVM are outperforming the other classifier, which is KNN. Okay, secondly, we have cross scenario. We have approach to, and also cross sensor case. So let's just focus on one of the subject, which is subject one, right? So in this case, let's say the training data is based on Empatica sensor, and our test data is based on Maxim sensor. So you can see the heterogeneity at there. And in this row for subject one, we are not using any transfer learning. So it's just basically a conventional SVM model. And in second row, we are using transfer learning. And here you can see the difference between accuracy in, without using transfer learning and using transfer learning. So obviously, transfer learning is improving the results here. And this is happening for other subjects as well. So the second case is cross-subject heterogeneity. So here, again, let's say subject one is our test data and other subjects are our training data. So again, there is this heterogeneity between different subjects which can impact results. So in this row, we are not using any transfer learning. In second one, we are using transfer learning. And you can see that in 3 out of 5 cases, transfer learning is improving the results, which is happening for other subjects as well. So generally in cross-subject case, transfer learning can be important. Finally, we have cross-scenario case, which is the heterogeneity between lab environment and real-world environment. So again, here we have the method without transfer learning and transfer learning. And you can see that here, transfer learning, it's not improving the results. So in this case, heterogeneity is not significant. So in summary, we show that the features captured from a single wristband accelerometer can be used to classify tasks performed by electrical line workers. And also we show that cross-sensor and cross-subject heterogeneities are very important and they should be dealt with using transfer learning. And finally, we show that cross-scenario heterogeneity is not that important in our case, and we can skip transfer learning and use conventional methods. Finally, for the future, we are going to use active learning when dealing with a limited number of observations, labeled observations. We are going to focus on real-time activity recognition. And also, we are going to focus on the case that null activities exist in our classification. Finally, I want to thank for the opportunity and the funding that was provided to us. Here we can see our references, and thank you so much.